The theorem is a function f is of bounded variation on closed interval ab if and only if f is a difference of two monotone real valued functions on closed interval ab. So if a function, a bounded variation function is given to us, we need to show that this function is a difference of two monotone real valued functions, and then the converse also. It's the if and only if case. So let's start with the proof. First, if it is given that let f be a function of bounded variation on closed interval ab, we need to show that f is a difference of two monotone real valued functions on closed interval ab. So for that, and let's take a subdivision of ab, a to be taken as x0 less than x1 less than x2 up to so on xk equal to b. So this be any subdivision of closed interval ab. Very fine. And now we need to define the positive variation to be, it is the summation on f of xi minus f of xi minus 1, because it is your positive variation, so I am using here positive sign, and I starts from 1 to k. And for the negative variation, the summation is on the same fxi minus f of xi minus 1, and because it is a negative variation, so I am using negative sign over here. And then what is t? It is the sum of n and p, right? So that is equal to, it is the summation on the absolute value of f of xi minus f of xi minus 1. There is a mod. It is the absolute value, right? It is a summation on the absolute value, right? Then we need to define PAB, that is the positive variation over closed interval AB. So this is the supremum of small p, which can be written as the capital P. And then this capital N, the negative variation over closed interval AB, this is the supremum of small n, which is written as capital N. And then TAB is the supremum of small t, which is written as capital T. Then it is obvious that the capital N is less than equal to the capital T. The total variation is always greater than equal to the negative variation and also the positive variation. And P is less than equal to capital T, right? And furthermore, the difference of P and N, this is equal to f of B minus f of A. Please remember this, this is very important. So from here, if I take n to the other side, I will be getting fb minus fa plus n. And because the small n is less than equal to capital N, because it is the supremum of small n, so I can write this further as it is less than equal to f of b minus f of a plus capital N. Can I write like this? Yes. And now if I take the supremum over all the possible subdivision, the possible subdivisions of closed interval AB, so I get this to be, this small p will be changed into capital P less than equal to f of b minus f of a plus capital N. And now since this capital N is less than equal to t, which is finite, the total variation is finite, so from here we say that therefore we can take this n to the other side, it is finite. So this is capital T minus capital N less than equal to f of b minus f of a. Please mark this as 1 because we need to show that capital P minus capital N is equal to f of b minus f of a. So to show this, I need to also prove that Now this fb minus fa is less than equal to capital P minus capital N. I need to show this, then only I can get this equality. So marking this as 1, we have already marked this first inequality to be as 1, and now let's get the second inequality. Again, since we know that the difference of small p and small n is equal to fb minus fa. In the first case, I have taken p to be on the left hand side. In this case, I am going to take n to be alone in the left hand side, right? So this is equal to p minus fb plus fa, yes? Just take negative outside or negative common, you will be getting this. And because the supremum of small p is capital P, so this p is less than equal to capital P, yes? So writing further this to be less than equal to capital P minus, okay, let me write this first. It is plus fa minus fb, right? And because this p is less than equal to t, which is finite, so I can take this p to the other side. But before that, I need to take the supremum over all the possible subdivisions. Now let's take the supremum over all the possible subdivisions over closed interval AB. The possible subdivisions of closed interval AB. So this small n is changed into capital N less than equal to capital P plus f of A minus f of B, right? And because this P is less than equal to T, which is finite, so I can take this P to the other side. So let's write this first. Since the capital P, the positive variation, is less than equal to the total variation, which is finite, so we can take this capital P to the other side, that is n minus p less than equal to f of A minus f of B. If I take the negative sign common, I will be getting negative sign over here and positive here. From here also, if I take the negative sign outside, I will be getting the positive sign here and negative sign here. So I am writing fb minus fa. And when taking negative common, this sign will be changed. Yes. So what we get? We get p minus n to be greater than equal to fb minus fa. So p minus n is greater than equal to fb minus fa, marking this as 2. So from 1 and 2 we get p minus n to be equal to f of b minus f of a. Because I need to show that the function fx is the difference of two monotonically increasing function, difference of two monotone real valued functions. So for this we need to show this. To get this fx, because this is fb minus fa equal to p minus n, right, over the closed interval ab. So this is from a to b. This relation is for the interval from a to b. Can I write this relation for the interval a to x? Yes, in the same way. Just substitute x in place of b. So thus it can be written as, from here we write that f of x minus f of a. I have substituted x in place of b. And this is equal to p minus n. If this p is for the interval, the closed interval from a to b, so this capital P is for the interval from a to x. Similarly, the negative variation. Yes, okay, fine. Okay, let me mark this as 3. Let's consider this to be gx, the function gx, and this to be the function hx. So let's take gx to be equal to p from a to x and hx to be equal to capital N for the interval ax. Because p and n, that is the positive variation and negative variation, these are monotonically increasing functions. For a function of bounded variation, the positive variation is always monotonically increasing, or it remains the same. It can increase or remains the same whenever we move along the x-axis, but it never decreases, right? So because the positive variations and the negative variations, these are monotonically increasing functions. So can we say that gx and hx are also monotonically increasing? Yes. So then g and h are monotonically increasing. So these are monotonically increasing functions. Remaining to write that these are also real valued. Yes, how these are real valued? Since what is gx? It is pax. What is hx? It is nax. We have just written that these are monotonically increasing. Now how these are real valued? Because these are equal to the positive variation and negative variation, if I show that these are finite, then we say that these are real valued also. So for the real valued functions, the values should be finite. So since this pax, it is greater than equal to 0, yes, and it is also less than equal to the total variation, and this further less than equal to total variation over closed interval AB, and we know that this is finite always. So which means what we are saying, that pax is finite, and because this is finite, so this becomes real valued function. It gives real values. So this pax is gx. Similarly, writing for hx, 0 is less than equal to capital Nax, that is hx, and is less than equal to total variation over closed interval ax, and is less than equal to the total variation over closed interval ab. Yes, we have replaced b with x. This does not mean that b is equal to x. We can take any x between a and b for the subdivisions. It can either be equal to b, it can either be less than b. And is less than infinity, it is finite. So which means hx is also real valued. So from these two we say that therefore g and h are real valued functions. G and h are monotonically increasing and also the real valued functions. So since our fx minus fa is equal to pax minus nax, that is equal to gx minus hx. So therefore I can write this, because I need alone fx. I have to show that this fx is a difference of the two monotonically increasing real valued functions. So let's take this fa to the other side. So this is equal to gx minus hx plus fa. Can be written as gx. If I take minus common, I am getting hx minus fa. Means subtracting the value fa from hx, this becomes your function. This is another function, and we have shown that okay, gx is monotonically increasing and also real valued. So hx minus fa is also monotonically increasing and is real valued function, right? So we have shown that this fx is the difference of monotonically increasing real valued functions. This is what is needed to be shown for the first way. And now to show the converse. Converse becomes, if fx is the difference of two monotonically increasing real valued functions, then we need to show that this fx is of bounded variation. On closed interval AB. This is the converse part. And when fx becomes the bounded variation on closed interval AB, if I show that TABF is finite, then only we say that the function is of bounded variation. Yes? Okay, let's prove this. The converse part. What is given now? If f equal to g minus h on closed interval AB with g and h, these are real valued increasing functions, and to prove that f is of bounded variation on closed interval AB. So starting from here, it is given that f is g minus h, where g and h are real valued increasing functions. So for this we can write, for any subdivision of closed interval AB, we have small t to be equal to the summation on, yes, the absolute value of f of xi minus f of xi minus 1. Now what is f of xi? We can write f of xi to be gxi minus hxi, right? So it is gxi minus hxi. Similarly, writing f of xi minus 1 to be gxi minus 1 minus hxi minus 1. So collecting the functions gxi minus 1 together minus hxi minus 1 together, right? And because I'm having the absolute value for this, I can write this further as this to be less than equal to the summation, the absolute value of gxi minus 1 plus the summation on h of xi minus h of xi minus 1. So further it is equal to, because g and h, these are increasing functions, right? So the absolute value for this is writing as it is gxi minus 1 plus the summation, the mod is changed into just hxi minus 1. These are positive, right? Taking the summation all over, we get gb minus ga plus taking the summation all over this, we get this to be equal to hb minus ha. So the inequality is moving from here. So on the left hand side we are having this t, and on the left hand side we are having this t. So writing this to be t less than equal to the right hand side gb minus ga plus hb minus ha, right? And now taking the supremum over all the subdivisions of closed interval AB. So when taking the supremum over all the possible subdivisions of closed interval AB, this small t will be changed into the capital T and is less than equal to gb minus ga plus hb minus ha. And because we have already shown that from here that gx and hx both are finite, yes, both are finite, so their values on a and b are also finite. So writing this further to be strictly less than infinity, and this is a total variation over closed interval AB. So we get that the total variation over closed interval AB is finite. So from here we say that, and when the total variation is finite, we say that therefore, this implies, therefore f is of bounded variation. Then only f is of bounded variation on closed interval AB. So hence we have shown the result both the ways. Let's again read the theorem. It is very important. A function f is of bounded variation on closed interval AB if and only if, that is for both the ways, if and only if f is a difference of two monotone real valued function on closed interval AB. So this is if and only if case. Both the ways you have to show, right? Okay, thank you. Stay blessed.